Number 1. The Hadean rock vapor sky. Picture yourself standing on the surface of the Earth 4.5 billion years ago. There's no soil under your feet, only a crust of barely cooled rock. And when you look up, the sky's not blue. It is not even black. It glows. The whole dome of the air shines with a dull orange light because the air itself is made of vaporized rock. This is the Hadean Eon, the first chapter of our planet's history, named in 1972 by the geologist Preston Cloud after Hades, the underworld. He chose the name because the conditions were hellish. The reality was worse. In this era, the young Earth was still being bombarded by enormous bodies left over from the formation of the solar system. These impactors arrived at 15 to 30 kilometers per second. When something that fast and large hits a planet, it does not just dig a crater. It vaporizes the impactor and a portion of the crust along with it, lifting it into the air as a gas of liquid rock. The Stanford geophysicists Norman Sleep and Kevin Zonley modeled the result. An impactor 400 to 500 kilometers across could create a temporary atmosphere of silicate vapor above 2,000 degrees Celsius. A sky that hot radiates heat downward, wrapping the planet in a blanket of glowing gas. As that vapor cooled at high altitude, it condensed, not into water, but into droplets of molten rock that fell back to the ground, still glowing. In 1991, Sleep, Zonley, and their colleagues James Costing and Harold Morowitz published a paper in the journal Nature showing how impacts like this could annihilate entire ecosystems, boiling away the whole ocean. The most extreme version came earlier. The giant impact that formed the moon, around 4.5 billion years ago, is thought to have enveloped the planet in silicate vapor at thousands of degrees. Such an atmosphere might persist for around 2,000 years before cooling. And yet between these catastrophes, the Earth was sometimes gentler. Zircon crystals from the Jack Hills of Western Australia, dated to 4.4 billion years using oxygen isotopes by John Valley at the University of Wisconsin, suggest liquid water existed surprisingly early. The geologist Mark Harrison calls this the cool early Earth, a world of brief, violent resets separated by long habitable intervals. The chemistry of that sky is alien to anything we measure today. Instead of nitrogen and water, it held silicon monoxide, oxygen, and metal oxide vapors, and its glow peaked in the near-infrared and visible light, so the whole sky shone like a dim star. We are not guessing. Astronomers now observe lava planets, worlds like K2-141b and 55 Cancri E, with rock vapor atmospheres and silicate rain right now. The pressure could exceed 100 times today's, crushing and cooking the surface at once. The energy of an ocean-boiling impact runs beyond 10 to the 26th joules, far past any human weapon. Some scientists argue life could only take hold after the very last of these impacts, an idea called the impact frustration of life. There is no shelter from a sky that glows. This is the ceiling of planetary violence, and everything that follows is a step down from molten rain. But every step still towers over anything we have built. Number 2, Hypercanes. Now bring the temperature down from molten rock to merely impossible. In 1995, the MIT atmospheric scientist Kerry Emanuel published a paper describing a storm that cannot form in today's world. He called it a hypercane. To see why it matters, understand what limits an ordinary hurricane. A tropical cyclone is a heat engine. It draws energy from warm ocean water, and the warmer the sea surface, the more powerful it can become. Today, the oceans top out around 30 to 31 degrees Celsius, a ceiling that caps the strongest sustained winds at roughly 300 kilometers per hour. Emanuel's modeling revealed something startling. Raise the sea surface temperature to about 50 degrees Celsius, and the storm's potential intensity does not climb smoothly. It jumps through a runaway thermodynamic feedback. The result is a hypercane with sustained winds approaching 800 kilometers per hour, close to 500 miles per hour, and a central pressure as low as 300 millibars. The strongest storm ever directly measured, Typhoon Tip in 1979, bottomed out near 870 millibars. The eyewall would punch into the stratosphere, 30 kilometers or more above the surface. What could heat a patch of ocean to 50 degrees? A massive submarine eruption or a large asteroid impact. The Chicxulub impact 66 million years ago may have superheated parts of the Gulf of Mexico enough to spawn these monsters. And here, the hypercane becomes a planetary threat. It would loft enormous quantities of water vapor and aerosols into the stratosphere, where they could damage the ozone layer for months or years, raising harmful ultraviolet light at the surface. A hypercane is smaller across than a modern hurricane, but far more intense, a tight, towering vortex. Emmanuel called it a theoretical limit derived from physics rather than read from the rocks. But the physics is sound. Winds of 800 kilometers per hour carry about 7 times the pressure of a Category 5 hurricane, enough to scour soil to bedrock and strip vegetation across whole regions. It runs like an ideal heat engine between a 50-degree C and a frigid stratospheric outflow, persisting as long as its heat source lasts, which over an impact-heated sea might mean days or weeks. Some researchers invoke fleets of hypercanes to explain how wildfire soot and impact debris spread so evenly across the planet at the end of the age of dinosaurs. For us, the numbers are off the chart. 800 kilometers per hour exceeds the design limit of every building, bridge, and dam on Earth by an enormous margin. Nothing engineered would remain standing, and a storm surge of tens of meters would erase a coastal city within hours of landfall. A hypercane needs a heat source to be born. The next event in our story delivered one in a single afternoon. Number 3, the Chicxulub thermal pulse. This is the event that defines the phrase in hours. 66 million years ago, an asteroid between 10 and 15 kilometers wide struck what is now the Yucatan Peninsula, releasing over 100 million megatons of TNT. Most people picture the crater, the dust, the long cold winter, but the first thing that happened in the first hours was fire from the sky. The impact threw molten rock upward, droplets called spherules, on trajectories that arced above the atmosphere and rained back down across the entire globe. As that ejected material re-entered the atmosphere, friction heated the upper air. The whole sky turned into a giant infrared radiator, glowing down like the element of a broiler for tens of minutes to a few hours. In 1990, the scientists Jay Malosh, Nicholas Schneider, Kevin Zanley, and Dan Latham published a model of this thermal pulse in Nature, estimating the infrared flux at the ground at around 10 to 12 kilowatts per square meter. That is like standing beside an oven set to broil, except across the entire planet at once. This is the leading explanation for one of the most haunting clues in the rock record. At the boundary marking the end of the age of dinosaurs, geologists find a worldwide layer of soot and charcoal, enough to suggest that a large fraction of all plant life burned in a geologically instantaneous event. The geophysicist Douglas Robertson and his colleagues argued in 2004, and again in 2013, that the heat pulse killed unsheltered animals directly, cooking them with radiant heat. This explains a strange pattern of survival. Animals in burrows underwater or otherwise sheltered tended to make it through. Exposed animals, including the dinosaurs, did not. Robertson later noted the heating may have been patchy, weaker where thick clouds shielded the ground. The spherules in that boundary layer worldwide are the fingerprint of the ejecta that caused the heating. At a site called Tanis in North Dakota, the paleontologist Robert De Palma has uncovered sediments that preserve the first hours after impact, including spherules lodged in the gills of fish. A separate snapshot of the aftermath, not the pulse itself. The thermal pulse came first, and only afterward did the long impact winter set in, as dust and sulfate aerosols blocked the sun for years. Sulfur from the vaporized Yucatan rock formed those aerosols and fell as acid rain. It was a deadly sequence. Flash broil the surface, then plunge it into cold, darkness, and starvation. Around 75% of all species vanished, including every non-avian dinosaur. We know the impact happened from the global iridium anomaly discovered by Loess and Walter Alvarez in 1980, the shocked quartz, and the buried crater identified by Alan Hildebrand and Glenn Penfield. The defining feature of the thermal pulse is its speed. No warning, no buildup. The heat simply arrived. And the next threat also strikes with almost no warning, except it comes from the sun. Number 4. The Miyake solar superstorms. Of every event in this video, this is the one most likely to end modern civilization in hours, and it has already happened more than once during human prehistory. In 2012, the researcher Fusa Miyake at Nagoya University was studying the rings of ancient cedar trees. In the rings that grew in the years 774 and 775 of the Common Era, She found a sudden, sharp spike in radioactive carbon-14, far larger than normal. The size of that spike implied a burst of high-energy particles 10 to 20 times stronger than anything our satellites have ever measured. She had found the fingerprint of an enormous solar storm. A second, slightly smaller event turned up in the rings from 993 and 994, confirmed worldwide and in the beryllium-10, trapped in polar ice. Then scientists found older ones. There was a very large event around 7,176 BCE, possibly the biggest of all, another around 5,259 BCE, and candidates near 660 BCE and 5,410 BCE. These are now the called Miyake events, recorded as synchronized radiocarbon spikes across multiple continents. The leading explanation is an extreme solar particle event, a giant flare far larger than the famous Carrington event of 1859, when telegraph wires sparked and auroras were seen near the equator. A Miyake-class storm may be roughly 10 times stronger. The mechanism is elegant. When energetic particles slam into the upper atmosphere, they transmute nitrogen into carbon-14, which trees absorb. The spike in the rings is the chemical fossil of that bombardment, and matching spikes of beryllium-10 and chlorine-36 in polar ice rule out any local fluke. Now consider what such a storm would do to us. The risk to the modern power grid has been estimated in the trillions of dollars, with blackouts lasting months or years. A 2013 report by Lloyd's of London estimated a Carrington-level storm could leave 20 to 40 million Americans without power for up to 2 years. The physics is brutal. The storm induces currents in long power lines that can saturate and destroy the largest high-voltage transformers, which take many months to replace. We have had a taste. In 1989, a far weaker storm blacked out 6 million people in Quebec for 9 hours. Satellites, GPS, and aviation could all be knocked out within hours of the particles arriving. That is the terrifying part. The most energetic particles arrive within tens of minutes of the flare, so the warning time is almost nothing. With several of these events in just the last 10,000 years, the odds on a civilizational timescale are not small. The sun has fired off civilization-scale bursts repeatedly while humans walked the Earth. It will do so again. We just do not know when. The sun is one threat from above, but the ground itself has drowned whole regions, and it did so fast. Number 5. The Missoula Glacial Megafloods. You can still visit the scars of this one. During the last ice age, a tongue of the Cordilleran ice sheet pushed south and dammed the Clark Fork River in what is now Montana. Behind that dam of ice, water pooled into an enormous body called Glacial Lake Missoula. At its largest, the lake held around 2,000 cubic kilometers of water, comparable to Lakes Erie and Ontario combined, held back by nothing more than a wall of ice. Ice is not a reliable dam. When it failed, the lake drained in a catastrophe almost beyond comprehension. The water burst out at rates estimated up to 17 million cubic meters per second. That is more than 10 times the combined flow of every river on Earth today, all at once pouring through the valleys of eastern Washington. In the narrow channels, the floodwater reached speeds of around 30 meters per second, over 100 kilometers per hour. It carved the landscape known as the channeled scablands, ripping the basalt into deep canyons called coulees, dry waterfalls, and fields of giant ripples. One of those dry waterfalls, called Dry Falls, is about 5.6 kilometers wide and 120 meters high. It dwarfs Niagara, and not a drop flows over it now. The story of how we learned this is itself remarkable. In the 1920s, the geologist J. Harlan Bretz proposed that these features were carved by a sudden, catastrophic flood. The geology establishment of the time was committed to slow, gradual change, and they resisted his idea for decades. The missing piece came from Joseph Pardee, who identified Glacial Lake Missoula as the source of the water. Bretz was finally vindicated, and in 1979, near the end of his life, he was honored for being right all along. The evidence is unmistakable once you know what to look for. Giant current ripples up to 15 meters high mark the floodplains, the signature of immense flowing water. Boulders, called ice-rafted erratics, some weighing many tons, sit far from where they belong, dropped by melting icebergs. This did not happen only once. As the ice dam reformed and failed again and again, the flood recurred. Layered sediments called rhythmites suggest 40 or more separate floods, each draining the lake in as little as a few days, with peak discharge lasting only hours. In the bottleneck at Wallula Gap, the water backed up over 120 meters deep. The energy of a single Missoula flood exceeded the output of all the world's power plants combined for its duration. And it was not even the largest of its kind. The Lake Bonneville flood in Idaho and gigantic floods from glacial lakes in the Altai Mountains of Siberia rival or exceed it. A flood on this scale, crossing a modern populated region, would destroy every dam, bridge, levee, and city in its path within hours, with no possible defense. This was meltwater unleashed. But the shape of a continent can manufacture violent weather every single year. Number 6. The Pangaean Megamonsoon. Travel back to the late Permian and Triassic between roughly 250 and 200 million years ago, when all the major landmasses were fused into a single supercontinent called Pangaea, stretching pole to pole across the equator. A landmass that vast does something dramatic to the weather. It generates what scientists call a megamonsoon, an amplified version of the monsoons we know today. The term was popularized in the 1980s and 90s by Thomas Crowley, Judith Parrish, and Fred Ziegler, building on foundational work by Paul Olson and Dennis Kent. The engine of a megamonsoon is the contrast between land and sea. In summer, the vast interior of Pangaea heated intensely, far hotter than any ocean. Hot air rises, and as it rose, it pulled in moist air from the surrounding sea, dumping torrential seasonal rains along the continental margins. In winter, the whole system reversed. Dry continental air pushed outward, and the interior baked under a punishing drought. The center of Pangaea became one of the largest and most arid desert zones in the history of the planet, a region of endless dunes preserved today as ancient sandstones. The seasonal temperature swings in that deep interior likely exceeded those of any modern continent, with scorching summers and bitterly cold winters far from the moderating influence of the sea. We can read the rhythm of this monsoon directly in the rocks. In eastern North America, ancient lake beds called the Newark supergroup record cycles of wet and dry conditions. Paul Olson showed they were paced by changes in Earth's orbit, the Milankovitch cycles, with a key beat every 20,000 years as the planet's axis wobbled, work that helped calibrate the entire astronomical timescale for the Triassic. Other clues confirm the picture. Thick deposits of salt and gypsum, called evaporites, record the intense dry season aridity, and widespread red beds, sediments stained by oxidized iron, indicate a strongly seasonal, often arid world. The monsoon was not gentle. Much of the year's rain likely fell in violent concentrated bursts during a short, wet season, with flash floods carving the land, followed by long months of drought, a feast or famine hydrology that shaped which life could survive. This baseline circulation is distinct from the Carnian pluvial episode, a separate wet pulse this channel has explored before. Computer models of Pangaea reproduce the megamonsoon reliably, which tells us it is a robust consequence of geography, not a guess. It peaked in the late Triassic and weakened only as Pangaea rifted apart in the Jurassic. The Asian monsoon already brings catastrophic flooding and drought to billions today. A megamonsoon is that system amplified across an entire hemisphere, alternating between region-drowning deluges and crop-killing droughts within a single year. Weather can be born from geography, it can also be born from a single plant. Number 7. The Azolla Event. Not every world-ending weather event is loud. Some are quiet and green. Around 49 million years ago, during the warm greenhouse climate of the Middle Eocene, the planet may have been tipped toward a colder state by a humble fern. Azolla is a tiny free-floating freshwater fern, the kind that can carpet a pond. Under the right conditions, it can double its biomass in just a few days. And during this interval, the conditions were extraordinarily right. At that time, the Arctic Ocean was a nearly enclosed basin, cut off from full circulation with the world's oceans. Freshwater from rain and rivers pooled on its surface, forming a brackish lid. That freshwater layer was perfect for Azolla, which bloomed across the entire surface of the Arctic Ocean, an ocean-sized mat of fern. We know this because of sediment cores recovered in 2004 during the Arctic Coring Expedition, part of the Integrated Ocean Drilling Program, drilling into the Lomonosov Ridge beneath the Arctic seafloor. The cores revealed a thick layer of Azolla remains spanning around 800,000 years of repeated blooms. Here is the crucial part. As the ferns died, they sank into the deep Arctic basin, where the water was stagnant and starved of oxygen. Without oxygen, they did not decompose and release their carbon back into the air. Instead, they were buried, locking their carbon away on the seafloor. Researchers including Henk Brinkhuis, Appie Sluits, and Jonathan Bujak studied this event and proposed that it drew down a large amount of carbon dioxide from the atmosphere. Some models suggest the reduction was dramatic, helping pull atmospheric carbon dioxide down from perhaps 3,500 parts per million towards 650, although the exact figures are debated. That drawdown may have contributed to the long-term cooling that eventually led around 34 million years ago to the first permanent ice sheets on Antarctica. A single fern, given the right ocean chemistry, may have helped nudge the entire planet's thermostat. It pulls off this trick with help, hosting a symbiotic cyanobacterium called Anabaena azollae that fixes nitrogen straight from the air, letting the fern thrive without fertilizer, a trait that makes Azolla interesting today for both green manure and carbon capture. The Arctic of the Azolla Event was warm and ice-free, with sea surface temperatures possibly around 10 degrees Celsius, utterly unlike the frozen one we know. Critics caution the drawdown's magnitude is uncertain, and that other factors, like the weathering of the rising Himalayas and changes in ocean circulation, also drove the cooling. But the lesson stands. The chemistry of the air is itself a kind of weather, and it can be rewritten by life. This event was slow by human standards. The climate can also flip in a single decade. Number 8. Dansgaard Oeschger Events. Imagine the temperature where you live rising by 10 degrees not over a century, but within your own lifetime. Then, imagine it happening again and again. That is what the climate did over and over during the last ice age in a pattern called Dansgaard Oeschger Events, named after the Danish scientist Willy Dansgaard and the Swiss scientist Hans Oeschger. There were about 25 of these events between roughly 115,000 and 12,000 years ago. Each event began with an abrupt warming. Over Greenland, temperatures jumped by 8 to 15 degrees Celsius within a few decades, and in some cases, within a single decade. That warm phase then faded gradually over centuries before the climate dropped sharply back into cold conditions. These events were first clearly resolved in the late 1980s and 90s in Greenland ice cores known as GRIP and GISP2, and later confirmed in a core called NGRIP. The thermometer is the ratio of oxygen isotopes frozen into the ice, which records past temperature. The abrupt shifts show up as sharp steps in the isotope curve, unmistakable jumps in the frozen record. What could flip the climate so fast? The leading explanation involves sudden reorganizations of the Atlantic overturning circulation, the great conveyor belt of ocean currents that carries warm water northward. Changes in sea ice and in the amount of fresh water entering the North Atlantic appear to switch the system between a warm mode and a cold mode. And these flips were not just local to Greenland. They correlate with climate changes around the world, including the strength of the Asian monsoon, recorded in the growth bands of stalagmites in Chinese caves like Hulu, and Sanbao, studied by Hai Cheng and Larry Edwards. There is even a link to the far south, a bipolar seesaw in which a sudden warming in the north matches a slower, opposite change in Antarctica. The defining feature is the abruptness. These were not the slow, grinding trends we associate with ice ages, but sudden jumps within a human lifetime. They tell us something unsettling. The climate system has tipping points, and it can flip from one state to another when pushed past a threshold. During the warmings, methane in the ice cores jumps too, reflecting expanding wetlands and shifting tropical rainfall, and the magnitude is confirmed independently by nitrogen and argon isotopes in the trapped air bubbles. For a modern society, a shift like this would transform regional temperatures, rainfall, and growing seasons within a decade or two, faster than our agriculture and infrastructure could adapt. This is exactly why climate scientists worry about abrupt nonlinear responses. These warmings had a cold twin, armadas of ice that chilled half the world. Number 9. Heinrich Events. The cold extremes of the last ice age have a name and a cause. They are tied to Heinrich Events, episodes when vast armadas of icebergs broke off the Great Laurentide ice sheet, that covered North America and drifted out across the North Atlantic. They are named after the marine geologist Hartmut Heinrich, who first described their traces in 1988. As those icebergs drifted and melted, they dropped the rock fragments they had scraped from the continent onto the seafloor, forming distinct bands of debris that geologists call Heinrich layers. 6 major events labeled H1 through H6 are recognized over the last roughly 60,000 years. The debris in these layers traces back to the Hudson Strait region of Canada, fingering the Laurentide ice sheet as the source. Each event released an enormous volume of fresh water into the North Atlantic as the ice melted, and that fresh water is the key to the catastrophe. Fresh water is lighter than salt water, so a sudden flood of it can cap the ocean surface and weaken or shut down the overturning circulation. The same conveyor belt that drives the Dansgaard Oeschger flips. When the conveyor stalls, the North Atlantic plunges into cold. And this is why Heinrich events coincide with the coldest stadial phases of the Dansgaard Oeschger cycles. There's even a larger rhythm, the Bond cycle, in which progressively cooler, warm events build up and culminate in a Heinrich event, followed by an abrupt swing back to warmth. What triggers the armadas is debated. In 1993, the glaciologist Douglas Mikael proposed a binge purge model in which the ice sheet thickens, its base warms, and lubricates, and it surges catastrophically into the ocean before regrowing. An alternative view holds that warming subsurface water destabilizes the floating ice shelves from below. The Heinrich layers can be centimeters to tens of centimeters thick across wide areas of the North Atlantic seafloor, and their effects reached around the globe, with signatures in the Asian monsoon, Greenland ice, and tropical ocean temperatures. During the largest discharges, so much land ice entered the ocean that global sea level rose by a few meters. Heinrich Event 1, around 16,000 years ago, and the younger Dryas cold snap that followed marked the turbulent end of the last ice age, and that younger Dryas is a story this channel has told on its own. The cooling from a Heinrich event could drop North Atlantic and European temperatures sharply over just decades. This is directly relevant today because the melting of Greenland is adding fresh water to the same North Atlantic, raising concern we could weaken the very same circulation. Ice in ocean can flip a hemisphere. Wind can bury it. Number 10. The Ice Age Loess dust storms. The last event in our countdown is hiding in plain sight beneath some of the most productive farmland on Earth. It is called Loess, a fine, wind-blown silt, and its vast deposits record some of the most persistent dust storms in the history of the planet. The recipe is simple and brutal. During glacial periods, advancing glaciers ground bedrock into a fine powder called rock flour. Meltwater spread that powder across barren, outwashed plains. And the cold, dry, fiercely windy glacial climate, with little vegetation to hold the ground down, lifted it into the air in titanic dust storms. The largest of these deposits is the Chinese Loess Plateau, covering around 640,000 square kilometers, with loess piled up to about 300 meters thick in places. Its layers record more than 2.5 million years of history, alternating between dust laid down during cold glacial periods and soils that formed during warmer interglacials. These alternating layers of loess and buried soil are one of the best terrestrial archives of the ice ages we have, and they line up neatly with the climate record from deep-sea sediments. Loess is not just a Chinese story. It stretches across Ukraine, Central Europe, and the Danube Basin, marking the southern margin of the Great Ice Sheets. In North America, it blankets the Mississippi Valley, Nebraska, and the Palouse country of Washington, some of it derived from the very Missoula floods we discussed earlier. The dust storms of the glacial maximi would have darkened skies and buried landscapes under accumulating silt. We can measure just how dusty the world became. Ice cores show that atmospheric dust during cold periods was many times higher than it is today, and the Antarctic core from Dome C, drilled by the European Epica project, shows clear dust peaks during glacial maxima. That dust did more than bury the land. By scattering sunlight and by fertilizing the oceans with iron, which boosts the growth of plankton, it may have helped draw down carbon dioxide, feeding back into the cold. There's a final twist that makes Loess deeply human. Once it settles and stabilizes, Loess becomes extraordinarily fertile soil, underpinning major agricultural regions today, including parts of China's grain belt and the American Midwest. The ground that feeds billions is the residue of apocalyptic dust storms. But Loess is also dangerous. It collapses and slides when saturated, and in 1920, the Hadean earthquake in China triggered massive Loess landslides that killed an enormous number of people. The modern dust storms off the Sahara and the Gobi are pale shadows of what the glacial world produced. A return to glacial-scale dust would devastate aviation, choke solar power, harm respiratory health, and damage farming across whole continents. The soil under our farms is the residue of storms that would end us. Step back from the individual catastrophes, and a single principle connects them all. Violent weather is a question of energy. The more energy a system has available and the faster it can release that energy, the more extreme the weather becomes. Impacts and eruptions inject staggering amounts of energy in an instant, which is why they produce the most acute events, the rock vapor sky, the hypercanes, and the thermal pulse. Ice sheets and oceans store energy more slowly, then release it in pulses, which is what we see in the floods, the Heinrich armadas, and the Dansgaard Oeschger flips. Look at how often a heat source sets the rules. A superheated sea is what makes a hypercane possible, just as the ordinary 30-degree ceiling of today's oceans is what keeps modern hurricanes in check. Salinity and freshwater control the ocean conveyor, which is why a flood of meltwater can flip the climate of an entire hemisphere. The shape of a continent forces the megamonsoon, and the chemistry of the air itself, the carbon dioxide that the Azolla fern pulled from the sky, sets the planet's baseline temperature. Weather, in the deep sense, includes the very composition of the atmosphere. A useful distinction runs through all 10. Some events are essentially instantaneous, like the impact pulse and the solar storm, arriving with no warning. Others are driven by feedbacks that build and then tip, like the carbon drawdown or the iceberg surges. That is exactly why some would end civilization in hours and others over decades. The metronome behind the slower ones is often the Milankovitch cycles, the slow wobbles in Earth's orbit that pace the glacial lake rhythms and the Loess layers alike. Everywhere we looked, the story was written in physical archives, ice cores and tree rings, loess and seafloor debris, confirmed by multiple independent records agreeing with one another. The deepest lesson is that Earth systems have thresholds. Cross one, and the system flips. Our modern climate is unusually stable and mild by the standards of deep time, and we have built everything we have on the assumption that the calm will continue. That assumption is the heart of our vulnerability. Modern infrastructure is engineered for the extremes of recorded history, not of geological time. Building codes, dams, and levees are designed for events that recur over decades or centuries, not the ones buried in the rock record. Nowhere is this more dangerous than in the electrical grid, the single most exposed system we have. A Miyake-scale solar storm could destroy the large transformers at its heart, and those take months to years to replace. The danger is not just the first failure, it is the cascade. When power fails on a large scale, it takes water treatment, fuel pumping, food refrigeration, and communications with it. Our supply chains run just in time with days of buffer, not months, and our economies are so interdependent that a regional shock ripples worldwide within hours. We've packed huge populations into coastal megacities, exactly where a hypercane surge would strike, and built an agriculture that depends on the stable seasons a Dansgaard Oeschger flip or a megamonsoon would destroy. We rely on aviation and solar power, both of which glacial-scale dust would cripple. The core problem is a mismatch of speed. These catastrophes arrive faster than our institutions can respond. We have had warnings. The 1989 Quebec blackout showed how a modest solar storm can darken a region, and in 2012, a Carrington-class storm crossed Earth's orbit, missing us by days. If a Miyake event struck today, the first hours would bring failing satellites and navigation, then surging currents in the grid, then the slow collapse of everything that runs on electricity. A synchronized global crisis is one with no outside help coming. The only real defenses are redundancy and hardening, and the difficulty is paying for events that are rare but extreme. Paleoclimate gives us the honest measure of what nature can do. The question that follows is obvious. Which of these could actually happen again, and which are already stirring? Not all 10 threats are equal in the present. Some are genuinely possible on human timescales, and some belong only to the deep past. Rank them honestly, and a clear picture emerges. Solar superstorms sit at the top. They are not a question of if, only of when, which makes them the highest near-term risk we face. Megafloods are entirely possible, whether from the failure of a modern dam, the sudden draining of a glacial lake, or the collapse of part of an ice sheet. Abrupt climate shifts of the Dansgaard, Oeschger, and Heinrich kind are plausibly within reach if we disrupt the Atlantic circulation, which is part of why scientists watch it so closely. Dust storms are already intensifying in places, driven by desertification and the misuse of land, though a return to glacial-scale dust would require a glacial-scale climate. Hypercanes need an extreme heat source, a major impact, or a massive submarine eruption, so they are rare but not impossible. The thermal pulse requires a large asteroid strike, which is exactly the scenario that planetary defense is designed to prevent, and 2 of our events are effectively off the table today. The rock vapor sky belonged to a molten young planet, and the Pangaean Megamonsoon required a supercontinent that no longer exists. Geology has moved on from both. This is where human action enters the story. We now run programs to find and track dangerous asteroids, and missions like NASA's DART have shown we can nudge one's orbit. We are improving space weather forecasting, beginning to harden the grid, and monitoring the Atlantic circulation for the slowdown the deep past warns us about. The useful way to think about all this is to weigh probability against consequence. The cinematic threats, the molten sky and the 800-kilometer storm, are the least likely to recur. The boring ones, the solar storm and the flood, deserve the most attention precisely because they are the most likely. Some of these we could prevent, some we could only soften, and some we could merely endure. The deep past does not just frighten us, it teaches us how to read the warning signs. How can we possibly know about weather that vanished millions of years ago? The answer is one of the quiet triumphs of science. The planet keeps records and we have learned to read them. Ice cores from Greenland and Antarctica preserve year-by-year layers, trapping ancient air in bubbles and recording temperature in their isotopes. Tree rings store the radiocarbon signature of solar storms, exactly how the Miyake events were found. And seafloor sediment cores preserve the debris layers of the Heinrich armadas. On land, the Loess and buried soil sequences archive the rhythm of the ice ages, and stalagmites record the strength of ancient monsoons in their growth bands. Impacts leave unmistakable fingerprints, the global iridium anomaly, grains of shocked quartz, and the spherules flung out as molten ejecta. Ancient aridity is written in salt, gypsum, and iron-stained red beds. The earliest crust and water are dated using zircon crystals, and isotopes of oxygen, nitrogen, and beryllium serve as proxies for conditions long gone. The real power comes from cross-validation. When tree rings, ice cores, and seafloor sediments all point to the same event in the same year, confidence becomes very high. Great international efforts stand behind the data, the ocean drilling programs, the EPICE project in Antarctica, the Greenland coring teams. Dating methods, from radiometric decay to the astronomical tuning of orbital cycles, anchor everything to a reliable timeline, and computer models of circulation and impact physics let us test whether our explanations work. The history of the field is humbling too. It took decades for the world to accept Brett's and his catastrophic floods, and the Miyake events emerged only from painstaking measurement. The record has limits, and uncertainty remains. But the method is sound, and it is the only way we can stand on a quiet hillside and reconstruct the day the sky caught fire. Here is the thought to carry away. The mild, stable weather we consider normal is the exception, not the rule. Earth's default setting includes skies of molten rock, storms of 800 kilometers per hour, and oceans that boil away or freeze over. We happen to live in one of the calm intervals, a stretch of unusual stability that began with the end of the last ice age. That brief calm is what allowed agriculture to take root and cities to rise. And somewhere along the way, we mistook a pause for permanence. The scale of deep time energy dwarfs everything we have built. A single Missoula flood outpowered all our power plants. And a single thermal pulse cooked a planet in hours. The thread that connects all 10 of these events is the crossing of a threshold, a system flipping from one state to another, and a region, or a world, transformed. The unsettling truth is that some of these threats are not gone. They are merely dormant. The sun will fire again. ice sheets can still surge. The ground can still drown. This is why memory beyond living memory matters. The geological perspective is the only one long enough to see the real range of what our planet can do. It is not a counsel of despair, but of humility, and of preparation without paralysis. The fertile soil beneath our farms, the steady current in our wires, the predictable harvest, all of it is borrowed calm, lent by a quiet moment in a violent history. There is a difference between fearing the past and learning from it. Return to that incandescent Hadean sky, the planet's birthright glowing like a dim star. We live inside the pause that came after. Weather is the oldest and most powerful force our world has ever wielded, and our survival has always depended on the part of it we cannot control. The storms are not behind us, they are only waiting.